significance. It is a cylinder, and the initial radius of the cylinder is 1 centimeter. Sorry, let's make that the diameter so that it matches my notes. And the force that I'm pulling on the ends of it is 100 kilonewtons. All right, questions about my handwriting or what is being asked?
That's meters or newtons?
That's newtons, that's meters, that's centimeters, that's meters.
Okay, 100 for
100 kilonewtons.
kilonewtons. Kilonewtons.
Kilonewton.
Yeah, that's what I said. You said kilometers, so.
Oh, did I? Oh, I apologize. It will not be the last time on this. All right, so first off, let's figure out what the stress is. Well, that's force divided by area. It's got everything in terms of just the basic units here. So what is kilo?
1,000.
Or 1,000.
All right, so we got 100,000. Area. Talking about we have a cylinder here, and talking about the cross-sectional area. In other words, a circle.
10 centimeters. 10 meters.
And what is the radius in meters?
Meters, 0.05 and 0.0. Half a centimeter.
That's the diameter.
Half the diameter.
Half a time.
Half a centimeter.
So 0.01 meters. So I think you got to it.
Yeah, eventually.
0.005 meters. So my area is pi times 0.005 meters squared. And what is this?
Seven point eight times 7.85 times 10 to the negative 7 meters squared.
I think somebody just corrected it. Units?
That'd be,
What did you say again?
Meter squared.
Meter squared, yeah. You corrected yourself. Meter squared. So I have 7.85 times 10 to the negative 7th meter squared. And so what is the stress?
Um, 1.274 times 10 to the 11 Pascal.
Is something else off then? Oh. That's not negative 7. I think it's negative 5.
Yeah.
Which changes that to -5, which changes that to 9. Because I was thinking I'd set the problem up so that we would not be past the yield strength, and so that's what, that was the red flag. So we're not beyond the yield strength there.
I think I added another 0.
Ah, that would do it.
Yeah, okay, so, okay.
It's like a misspelling. All right, so we are within the elastic limit, or close enough to that. We're assuming that the yield strength and the limit of proportionality are close enough to each other. How much will it stretch? Since we're still in that elastic region right there, if this is the amount of stress I'm applying, let's figure out what the strain is. I know that as long as I'm still within that elastic limit here, this tells me, this guides me into how much strain there is. Because I know that stress divided by strain should be equal to the Young's modulus. If within an elastic limit. And so my strain should just be my stress divided by Young's modulus. So I have 1.274 times 10 to the 9th pascals divided by Young's modulus of 6.89 times 10 to the 10th pascals.
I got 0.018.
0.018.
Yes.
Okay. Units?
Pascals. But no, it's gonna be none, because there's no unit, because
Sorry.
both of them is Pascals. You know, that cancels out. No units.
All right, so I have 0.018. Anyone else get the same? Or just all have confidence in what John says? Ronald doesn't.
Well, I'm gonna check.
The old Russian proverb, trust but verify. I don't know if it actually is a Russian proverb, but during the Cold War years, those kept being attributed to being a Russian proverb.
Okay.
You got the same thing? All right. Half the class agrees. All right, so now we have to figure out how much it actually stretched there. So I have this, because ultimately I'm trying to figure out, well, I have my longitudinal stress now, so this is 0.018. But in order to figure out the transverse, we need to actually figure out the physical length that is now stretched. Let's see, I think this is still on camera. So let's figure out the volume, because I'm making the assumption that the volume stays the same, and that's going to help me figure out how thin it becomes. So my initial volume equals my final volume. So how do you find the volume of a cylinder?
Area times height.
So we've got our area times height or length, whichever one you like. I'm going to go with length just because that's the language we were using before. So initial area times my initial length is equal to my final area times my final length. My initial area, we figured out, was 7.85 times 10 to the negative 5th, times my initial length, which was 10. So that becomes 7.85 times 10 to the negative 4th cubic meters. So now we actually have to figure out what is my final length.
once you multiply it by multiply the initial length by the string.
Well, actually, what will that tell us? Yeah, we need to do that, but if we multiply the initial length, let's just go ahead, since we have to do it anyway. So 10 times my initial length of 0.018, try that one again. My strain times my initial length, and that gives me 0.18.
0.18.
What does that number tell us?
How far
Far.
it's stretched, how the change,
Oh, yeah, sorry, brain burp. So what are the units?
meters.
So my new length, area final times my new length is now 10.18 meters. So what's my final cross-sectional area?
It'll be half of that. Well, section.
Or how would you find it for those not doing using a calculator?
You would, divide the volume by the,
Yep. The math problem,
Yeah.
7.85 times 10 to the negative fourth
Divide.
equals A times 10.18. That's the math problem. And what did you get for the area? I think 7 point something.
7.71 times 10 to the negative fifth.
Square meters. What can we get rid of? Actually, get rid of this part. And that's equal to pi r squared. So that was 7.71 times 10 to the negative fifth square meters. That's equal to pi times my final radius squared. So divide by pi. And then take the square root. The number I wrote down is just one I did in my head. I'm assuming somebody will do it, use a calculator and tell me the actual value.
What is, oh, this is the final radius?
Yes.
Okay.
Ten to the negative 5 over 3.14. And that's the square root of it. Let's see.
Oh, that's right?
Almost right, 0.04, 0.00495
95. All right. Units?
meters, or, meters.
Your second thoughts.
Centimeters?
This was square meters here.
Okay, so meters.
Yeah, meters. Quick check here is that it is less than what our initial radius was, so feeling good about that. But we need to figure out Poisson's ratio. That's ultimately where we're heading. So we need to figure out what is the transverse strain. And so transverse strain would be the change in the transverse length over the change in, over the initial length. And I'm just using lowercase here for the skinny ways. I got, so that I'm making it little l, and this I'm making big L. So when I'm finding change, I got my final value there, and I got my initial value here. How do I find my change?
What is the strain equals the change in what is that? What is that?
This?
Yeah.
Change in the transverse length over the initial transverse length. I guess sub I or sub O.
I guess you just take the initial rate or initial diameter subtracted from the final diameter.
And what do you get?
You're gonna get 1 minus, maybe what, 9.99, it's like 1/10 of a centimeter.
But you said 1 minus.
1 centimeter minus 0.99 centimeters.
Ah,
Yeah.
okay. So you want to put it in centimeters, so
We're gonna have
you said 1 centimeter minus,
0.99. 0.01 centimeters.
something's off. Nope, sorry, another brain burp. I appreciate you going for it, however, there is a mistake there.
Oh, darn.
It's a small one, but it's a crucial one in the general scheme
It's
of
not in
physics.
centimeters, it's in meters.
Yeah, okay, so we can do it in terms of meters, just 0.0001 meters. There's a more fundamental math issue.
Should it be the final minus the initial?
Yes. Change always final minus initial. So negative. So in terms of meters, negative 0.0001 meters divided by what is the initial transverse length?
1.
We'll throw some units in there.
I think I'm lost. I don't.
What was the initial length here, going this way?
Oh, 1 centimeter?
There we go, 1 centimeter or 0.01 meters. And there's something off. And it could just be a rounding thing.
Is it the 495? Because it might be 496.
That would explain some of it. Let's see.
Negative
No, I had-
0.01.
I had 467 instead of 495. I'm just trying to see, but I also took that 0.18 and I took that out farther. So the new radius is 0.004953. Nope. pretty much in keeping with that. Oh, okay, no, sorry, wow. It's one of those days. So this becomes .01?
Negative .01.
Negative .01, okay? We haven't answered the question yet, that's,
What was the question?
what's Poisson's ratio? We just found the transverse strain. Negative, like transverse strain, negative .01. By longitudinal strain, .018. And so we end up with a Poisson's ratio of 0.5 something.
Repeat.
0.5 repeated. All right.
Wouldn't that be a negative?
No, because.
Oh, that's right, that's right.
Yep.
Yeah. Come on.
And the fact that the Poisson's ratio is positive is telling us that as it gets longer, it gets skinnier. Now, questions on this before we do, want to talk more general, make some general comments about Poisson's ratio. Okay. All right, so we got a value of 0.55. We did make, again, the assumption that the volume doesn't